pleasure to have invited Dr. Orazio Gallo to give us a wonderful talk titled as Depth Estimation from RGB Images with Applications to Novel View Synthesis and Autonomous Navigation. So let me give a quick, a brief introduction to Dr. Orazio Gallo. So Orazio is currently a principal research scientist at Nvidia Research at the US, and he's interested in computational imaging, computer vision, deep learning, and in particular, of course, the intersection of the three. So alongside topics such as view synthesis and 3D vision, his recent interests also include integrating traditional computer vision and computational imaging knowledge into deep learning architectures. And previously, Orazio's research focus resolved around tinkering with the way pictures are captured, processed, and consumed by the photographers or the viewers. Orazio is also an associate editor of the IEEE Transactions on Computational Imaging, and he was also an associate editor of Signal Processing Image Communication from 2015 to 2017. Well, since 2015, he is also a member of our IEEE Computational Imaging TC as well. So without further ado, let me just pass the time to Orazio, and let's welcome his wonderful talk tonight.
Thank you so much for the introduction, Biham. Yeah, I'm really excited to be here. Good morning to everybody who's in the United States, and afternoon or evening, depending on where you are in the world. So as Biham said, today I'll be talking about depth estimation, in particular for two challenging cases, and both driven by a specific application. And compared to other talks in this series, this talk may have a bit more of a computer vision flavor to it. And that's because computer vision and computational imaging are very strictly related, and my interests, as Biham was also saying, are at the intersection of the two. But hopefully I'll be able to pique your interest regardless of this. So I don't really think I need to convince people about the importance of depth, but just for context, the most common and cheapest setup that we always rely on to interact with the world is to use one or more RGB cameras and capture the world to get a 2D representation of the 3D world. And if we had depth, we could do a number of things. For one, and this is perhaps more obvious, we could improve the interaction with the world, right? Think of navigation, robotics, even scene understanding. 3D is a much more rich information than 2D. But at the same time, we could also improve the process of doing imaging and doing photography, right? In particular, I'm thinking of novel view synthesis approaches. You can think of a large number of applications such as synthetic depth of field or re-rendering scenes with different types of cameras. And so it's really using depth is a very valuable tool, right? And so the question may be, why not using some of the many dedicated hardware solutions to estimating depth? And that's, in my opinion, they produce very high quality depths, and they're very important in different sectors, but they tend to be more specialized, less widely available, more expensive, oftentimes low resolutions, and most importantly, they are an additional sensor that you may have to carry. And we all know that nowadays we have a very powerful camera in the pocket of our pants every time we leave our places, right? Because our cell phones offer that. And so this to me is a very strong motivation to investigate ways to estimate depth directly from RGB images, right? And so today I'll be talking about two specific challenges related to estimating depth from images. One is when you use a single camera, monocular camera, you move it around and the scene is dynamic, right? This breaks all of the geometric constraints that are traditionally used, and it requires some tricks to be solved. And I'll talk about this specifically in the context of novel view synthesis, which is an area that I'm really interested in. And then in the second part of the talk, I'll spend a little bit more time, hopefully, on stereo-based depth estimation, where the problem of dynamic scenes is less important because the two cameras capture the scene at the same time, but there may be a very tight time budget, and even more importantly, this time budget may change over time depending on what the application. And I'll focus a little bit more in this case on depth for autonomous navigation. So without further ado, let's start with the first step, which is based on the first part of the talk is based on a paper that my collaborators Jae-Shin, Ki-won, Yoon-soo, and Yan published with me at this year's CVPR. And here, the idea is to be able to create novel views of a dynamic scene, but using only a single camera, as I was describing before, right? So, novel view synthesis is becoming a mature technology. Here, you can see a few examples from state-of-the-art methods from the last few years. And all of these images are rendered. They are not real images, or at least most of these images are. The input to these algorithms is a subset of images of the scene, and that's it. And then these algorithms produce these like compelling, engaging pictures, and they look really photorealistic, right? And so if the results are so good while we're still working on this, well, there's a number of open issues. One that you may notice by looking at these images is that all of these scenes are static, right? And my question is, for everyday casual photography, wouldn't it be much more attractive and useful if we were able to handle sequences like this one, where both the scene and the camera are moving, right? So if we could handle scenes like this, well, for one, we would enable the photographer to just use a single camera and unleash his or her creativity, but we can also create different types of visual effects, like this bullet time effect, right, which was popularized by the movie The Matrix. And you can see that here we can freeze the dynamic part of the scene and move around the virtual camera, or we can play both together. In fact, we can even do something that we call space-time navigation, where we disentangle the time axis and the space axis and explore them independently of each other. So we're moving the camera while the content is also moving. And so, incidentally, these last two videos are results from the method that I'm going to describe now. And to understand why this is so difficult, let's look at how novel view synthesis is usually done. So you usually have a real scene. You take a few input images of the scene from different perspectives, and then you need to generate a new image that looks as if it was taken from a different positioning space, right? And all you have, again, are these captured images. And so if you can estimate depth, then the most powerful way of solving this problem is to say, look, I need to generate this patch in the novel view. I know the corresponding depth to this pixel. I can project it into the scene. From the scene, I can project it into the input cameras, and I can get the value, the information for the pixels directly from the input cameras. You know, I just need to do some depth-based warping to get the value that I need to paste in this novel view, right? And so the key is that we need to be able to estimate depth. And as I said before, when the scene is moving, it's not easy with a single camera to estimate depth. So here I'm showing a very simple sequence of a UPS truck moving while a camera is moved. At the bottom, you can see the camera position as estimated by a state-of-the-art structure for motion algorithm. And you can see that the camera moves roughly in a circle, and you can see that the structure for motion algorithm cannot find any points in the dynamic region. In fact, on the right here, you see the depth maps associated with each of these images, as estimated from the whole sequence. And two things to observe are the obvious, the part that of the scene that is dynamic. The depth for that part of the scene cannot be estimated correctly. But you can also notice that there are the typical issues of match-based depth estimation, which is textureless regions are not handled well, and artifacts such as the reflections on the windows can throw off the depth estimation as well, right? And so these are even independent of the fact that the scene is dynamic. So if you've been following the literature of depth estimation algorithm, there's this new trend of single image depth estimation, which is actually almost mind-blowing how well it works. So this is a picture that I stole from the Maidas paper. And what you can see here is that and each row shows a different algorithm. And all of these algorithms, what they do is they take the image in the top row, one single image, and they produce a fairly impressive estimation of depth from a single image. Of course, they are not using geometric constraints because we only have one image, but instead they learn image priors from a large training set, right? And so a couple of things to note right away. Again, they are impressively good, these results. There are no regions for which we don't have an estimate. Even though there's textureless regions in these scenes, we still have an estimate for each pixel, right? And so this is very promising because maybe this can offer complementary information to what we saw before, and maybe we can use it to solve our problem. You may notice that also that the relative depths of different layers in the scene, for example, the woman in front is correctly identified as being in front of the person in the background. But of course, as you can imagine, this depth is not metric, right? Because there's no way to infer that information. So can we use this? Can this be our solution? Is this good enough? These are two very recent methods from the last CVPR and from a recent talk paper. And they show all of these videos that you see are generated by taking a single image as input, estimating depths from that image, and then using this depth to re-render the scene from different perspectives. And these are really impressive results. I particularly like the fact that the results on the right, which are from the 3D photography paper, the citations at the bottom, these are actually archival images. They're not images that they captured, right? So these, you can go with your favorite historic moments and generate something like this. And so is this good enough for us? Well, the problem is that these methods use only one image, right? And they only take as an input one image, which means that when you then go to multiple images, the fact that the depth is not metric can cause issues. So this is the same sequence that I was showing before, and you can see that indeed we have a depth for each pixel. The depth looks reasonable in any one frame, but when you compare different frames, you see that there's flickering, right? You see that the depth is not in the same range. It's not the same pixel, or rather the same point in the scene is not estimated to be the same depth in all the frames. And so the key intuition of our method, and this is really, if you take one message out of this first half of the presentation, this would be it. The key intuition is, well, why don't we combine the best of both worlds? So we know that, we know that multi-view stereo-based depth is really good in some regions, the static regions and the regions where we have texture. And we know that single image depth is more complete, and it doesn't really care for the scene being dynamic, because in a single frame, barring blur, everything is static by definition. We can combine these two into a single depth, which you can see here, that is hopefully complete, metric, and stable over time, right? And we don't need to go into too many details, but the key intuition is that we take as input these three pieces of data, which are the RGB image and the two depths that I just described. And then we also have a mask that tells us which regions are static and which regions are dynamic. This mask for now is manually defined, but you can think of a semantic segmentation algorithm that can be used to replace the manual part. Anyway, with this, we know what parts of the scene are static, and we know that for those parts, the output depth that we generate needs to agree with the multi-view stereo depth, because that's the magic part. That's where we know that the multi-view stereo works well. And so we just train this network to make sure that these two agree, the final depths and the multi-view stereo depths agree in the static regions. Then we also, of course, know the dynamic regions and where they are, and we enforce that the output depth be consistent with the input single image depth. And then we also enforce the regularization term, essentially the Laplacian, to make sure that the normal Laplacian, to make sure that these two regions that there's a smooth transition between these two regions. Now, this method can be seen as upgrading the depth to as close as possible to be metric, the depth from the single image depth estimation, but it doesn't necessarily, there still may be some issues with over time, right? With the estimation over different time stamps being different. So what we do is we also take frames from different timestamps and we compute the optical flow between them. Now, with the optical flow and the depth that we estimated from the previous step, we can estimate sync flow, right? We can just essentially project this optical flow with these two depths into space. And then what we can do here is we can say, we can use the assumption that, or the observation that the 3D scene motion should be, in general, smooth and slow, and use that as a regularization on the scene flow and backpropagate the error across all of the network, from including the first part that I showed before. And so now, we should have had computed complete, metric, and stable over time depth. In fact, I'll show you a few results. This is, we also have a lot of numerical results in the paper, but I try to avoid too many numbers in the slide. You can get the same take-home message from here. What you're looking at here is, in the first column, there is one image from a number of dynamic scenes. The second row, second column is what we call the ground truth, which essentially we captured by using this camera rig that you see at the bottom. Here, we had 12 cameras that were synchronized, and because they were synchronized, effectively the scene at each timestamp was static, right? So we have 12 cameras for each, 12 views for each timestamp. And what you can notice is that even in that case, a state-of-the-art multi-view stereo algorithm has the issues that we described before, for example, in the lack of texture, or when the surface is not Lambertian, like this balloon, or these windows. And in contrast, our method, which you see in the third column, is complete, agrees with, for the most part, with the ground truth depth, and doesn't have those artifacts. Of course, if you do multi-view stereo on the dynamic sequence, you get similar results to the ground truth, but with more artifacts due to dynamic to the dynamic objects. And just maybe another quick observation is this is a different single image depth estimation method, mono depth, and it produces very reasonable results. They are edge aligned and the relative depths are correct, but as you can see, the scale and the range are completely different, right? And so with this depth, we can then tackle our end goal, which my PowerPoint does not want to show. Oh, there you go. Here I'm showing a few videos of synthesized images where we essentially take dynamic input sequences, we estimate the depth in the way it was that I just described, and we render new images. There's a little bit, there's a few details that I'm not covering about how we do the rendering. It's not, I don't think it's the most interesting part of the paper, and that's why I focused on mostly on the depth. But we have a second deep learning module that takes the input images and learns to combine them using a simple loss. So so yeah, this is what I wanted to say about depth estimation for dynamic scenes. And so the take-home message really, in my opinion, is that these single image depth estimation are really powerful tools. They are not good enough to perform rendering because they are not metric depth, but they are complementary to standard geometric constraint based depth estimation, and therefore they can be used in concert with them, and they can fill the voids that standard state-of-the-art depth estimation methods have. And so with that, I wanted to talk about a second issue with depth estimation, which is the case of stereo, but when we are pressed for time. So let me describe this. This is based on a paper that my superstar collaborator Abhishek and Alejandro, Kiwan, Jan, Pradeep, and I published at this year's CVPR. We call it by3D for binary 3D. And essentially, it's a fundamentally different way of thinking of stereo. And I'll try to convince you about that. Now, I know that this is probably for many people may say, well, you just argued for using the single most common and widespread scenario, which is a single camera. Now you're talking about stereo. Well, I agree that stereo is not quite as appealing as a single camera, but it does. It is a different way of solving for dynamic scenes, right? Because again, these two cameras capture the scene at the same time, are synchronized, and therefore the scene is effectively frozen. And arguably, it's still closer to a single camera. The images it produces images is still relatively cheap compared to many dedicated solutions for depth estimation. And so, and it's also relatively widespread, right? And so maybe some people in the audience don't focus as much on stereo, so I will cover a few of the basics, and I apologize to the ones who are very familiar, because these are going to be very basic concepts, but I want everybody to be on the same page. So the problem of stereo is you have two images as here, the left image and the right image, and you want to estimate a depth map, which means you want to estimate for each pixel the corresponding depth, right? And so this is a very well-studied problem, and all of the existing algorithms build on the exact same principle, which is that when I look at the image of a scene captured from a camera, I cannot know, for example, for this red pixel, I cannot know the actual depth, because all of the points, the 3D points along this red line project to the same pixel, right? However, if I use a second camera, now I can solve this ambiguity, right? And what's very interesting to notice is that as we move a 3D point along this line, the projection of the 3D point is also moving on a line in the second image. And this line, which is called a epipolar line, is just a function of the position of the two cameras, right? And so what this means is that in order to find the depth of a point, we need to find corresponding pixels in two images, and this observation allows us to only look only have one free parameter along the displacement along this line, right? Even more, we can rectify the images, which essentially means we apply some simple geometric transformation that aligns these epipolar lines with the rows of the image levels. And then we stack them all together. So in this volume, as you move from front to back, you're using a smaller disparity, which means you're going from close to the camera to farther from the camera. And then you can compare the other image, in this case, the left image, with all of these layers, right? And you can compute a cost. And what this cost tells you is, well, where the correct match is, right? So if we look at a particular pixel, say pixel Q in this volume, and we look at the cost across the different disparities, well, this is not really the cost that you observe. This is the ideal latent cost. What we do really is we sample it at the different disparity levels that we tested in this volume. And what we do is we say, okay, all of these have, at each disparity level, we have a different cost. The higher the cost, the lower the probability that that is the correct match. And so we can estimate the match by simply choosing the most likely point is the one with the lowest cost, right? So just to make sure we are on the same page, instead of finding a match for one pixel by moving along the line and then doing the same for another pixel and doing the same for another pixel, we are shifting the whole image, and then we're looking in the disparity direction and finding the layer at which the reference image and the target image match, right? So this is very cool, and it works very well. But what happens is if, say, I want to trade accuracy for latency at inference time? Well, so first of all, why would I want to do that? Well, consider the case in which you're driving on the highway, right? You're driving at 70 miles per hour, or let's say 65 miles per hour, since we all respect speed limits. I would argue that low latency is much better than accurate estimation, right? In other words, I'd rather know that there is a potential obstacle somewhere 80 meters away from me, but find that out like within a few milliseconds, than knowing that there's exactly at 84.6 meters, but I find out 10, 15 milliseconds later, right? And so I think there is value in getting a much lower latency, but potentially less accurate estimate, right? And so can we do that with the setup that I just described? Can we sample this distribution, this cost, at sparser locations? Well, we can sample, but then we get a totally random result, right? And we're not getting something that is slightly off. We can get any value. The value that we get is among the different samples that we took out is the one with the lowest cost, right? And similarly, let's say that now instead of driving on the highway, I'm trying to park my car. And now I don't care about very large depth. I don't care for stuff that is 100 meters away, or in other words, that has a very small disparity. Remember, disparity and depth are inversely proportional. But I do care for stuff that is closer to me with a much higher resolution in depth, right? And so what happens in this case is similar. Like any existing algorithm that looks for the most likely match will find a match within the samples that you gathered. And so in this case, again, it will be one of these 4 samples, right? So it will be if the pixel's depth is within this range, then you're fine. If it's outside of this range, it will still be mapped to this range, right? So how can we go around this problem? We make a simple observation. If you take the left image and then you choose a certain disparity level and you use it to shift the right image, right? I'm flipping between the two. What you can notice is that depending, so in this case, the disparity level corresponds to a depth somewhere between these two circles that I'm showing, right? And what you notice is that depending on whether the pixel is in front or beyond the disparity level, the displacement will be in opposite directions. And so this is our key idea. All of the methods that I showed, or rather the standard way of solving for stereo, is to regress the absolute value of the disparity. We propose instead to classify the disparity as the direction of the disparity. So that if the disparity points to the left or to the right, and just perform that as a series of binary classification. So in the case that I'm just showing, where the disparity is roughly in between these two pixels, we would like to get a binary map that tells us which pixels are in front, the white pixels, and which pixels are beyond the black pixel, the disparity level that that we picked, right? And so these are the black pixels. And so if we go back to what I was describing before about standard stereo, excuse me, standard stereo matching essentially finds, it's looking at the probability distribution and is trying to find the maximum value, which means, again, that you need to sample the maximum value if you want to find it. What we do is we estimate the probability that the disparity of a pixel is greater than a certain value, right? And so now, wherever you sample, you do get some information. So let me, the way we actually, so of course we use deep learning to do this, and the actual architecture of the network I find is like not as crucial. You know, we just use state-of-the-art standard techniques. What we do is we have left and right image. We extract features with the same you know, encoder network, and from then we take the features from the right image, and we take as input a disparity level, and we work those images, those features based on the disparity level, and then the work features and the left image, the other image, the left features, the other features, get input to a segmentation network, which performs this segmentation that I just described, right? And one thing to note is that we are training it with binary cross-entropy loss, which essentially just says it's the standard way to train a binary classification task. But the point is that this is trained independently of the disparity. In other words, the way we generate training samples are by randomly sampling a stereo pair and a disparity. And so this network learns for any disparity. In fact, what we can do is we can, just for the sake of it, we can right now swipe all of the disparities starting at 0, which is infinity, and coming towards the camera, right? So we'll start from the disparity 0 all the way to disparity infinity. Well, not quite infinity, but towards that. And what you'll see here is a video of this segmentation mask that I was talking about, where pixels are identified as white if they are in front of the plane that we are currently looking at. And so, oops, this is not what I want to do. Let me go back and do this. And now you see that as the plane comes closer to the camera, more and more pixels get identified as being beyond the plane, right? And then if we look at pixel Q, we see that we see that its actual disparity or depth is the disparity at which it flips between being in front or behind, right? And this is probably giving you the intuition of how we can actually estimate depth from this approach. So let's look how this works. So we have, in this case, we have a left image of a stereo pair. For one pixel Q, we have this, as we go through through all of these planes, we would be able to observe a function like this. It says, you know, it says that the pixel is beyond, that the pixel is this is closer. So the pixel is beyond, and then it comes in front. And if we sample this at a certain disparity, we get a confidence method because we use binary cross entropy loss. We really get like a continuous value for each pixel. So some pixels, like the pixels that are blurry, are closer to this region, for example. And then we can threshold it to get a binary method, right? So this is what I described before. I would argue that this is already useful information in the sense that it already tells you, for example, in this case, that if this is the road in front of you, there's nothing to be worried about. And we can compute these in like very fast, like in an image of this resolution, we run it in 5 milliseconds compared with the state-of-the-art stereo algorithms that run at slower than real time. So like 30 to 60 frames per second. Up to 30 frames per second, if that, if not, they take longer. But we can do more, right? We can sample at many locations, and each of these locations gives us a different binary segmentation, binary confidence map, right? Let me play this again. You see that as the disparity increases, more and more pixels are classified as being beyond. And now this, if you noticed, this is really this P of D greater than D is really the complementary of a cumulative distribution function, right? So we can compute the probability of a pixel being in a particular bin between these particular interval between this sampling by subtracting the corresponding probabilities. And so we can combine, I'm playing one more time, we can combine all of these observations, which are all independent of each other, right? And we can do any of them at any location and any number of them. And we can combine them into what we can call a quantized depth map. Now notice that this quantized depth map has a number of levels that can be variable, that the specific values can also be varying. We don't have to have them distributed over all the range, and we don't have to have them distributed uniformly. And this gives us a much richer information than binary depth map at a fraction of the cost of a full depth map. And notice that here we are trading quality in the depth direction. In terms of spatial resolution, we are as high as the input image, right? And so this is, I just wanted to show you really quickly for different levels, 4, 8, and 16 levels of quantization. You can see that, and here, so each, the first and the third column are ground truth quantization, and the second and fourth are our estimation. You know, they are very comparable. The ground truth will obtain by taking the ground truth depth map and quantizing it in the same number and in the same bins that we use for ours. But what I want to point out here is that even at 4 or 8 levels, you already get a fairly good understanding of what's in scene, right? You don't get the accuracy that you get at 16 or potentially at full resolution, but you get a good information, right? And actually, I don't want you to look at all these numbers. What I do want you to focus on is that as we increase the number of levels in the depth that we estimate from 2 to 4 to 8 to 16, the time also increases, but it increases linearly. And these are essentially independent, although because some parts are shared, the time doesn't scale exactly like the number of levels. But you can see that in even at 8 levels, which already gives us a pretty good understanding of the scene, we can run at much faster than real time, right? These other numbers, if you're curious, are like just a measure of quality. The higher the better, and you can see that our method does slightly better than other methods, but these other methods run in at least 60 milliseconds or more, right? So that's where the advantage is. So how do we, so this is for quantized depth. How do we, I mean, sometimes we will want to have full continuous depth, right? How can we do that? Well, it's not very different. We can take exactly what we had before. So this, we take the features directly so that we don't have to recompute it for every disparity. And then we take a set of disparities. And this essentially gives us a set of these maps, right? Which we then combine into a volume. And then it doesn't matter that much, but we do some 3D regularization just because, you know, if you do have information about neighboring disparities, you may want to use it to regularize. And then you get this, now you observe something very similar to what I was describing before, which is the full complementary distribution function. And so now the problem is, how do you train this, right? Because you want to train this end to end, but now you cannot train with that by taking the difference of subsequent disparity levels. And so what we noticed is that you can actually use the area under the curve. Let me elaborate. Let's say that you had a perfect profile. This is a plot like the ones that I was describing before. And it's exactly 1 all the way to the correct disparity. And then it drops exactly to 0 at the exact disparity, right? If that's the case, you can see how the disparity level, it's really the area under the curve because it's 1 multiplied by the number of disparities at the bottom, right? And so in this ideal case, we get that the area under the curve is exactly the disparity that we're looking for. More generally, we find that the disparity, sorry, this confidence, this probability drops linearly around the disparity level. But in this case as well, because if you look at this triangle and this triangle, they are the same, essentially the disparity, not essentially, the area under the curve in this case is still exactly the disparity level that we're looking for. So up to here is 1 multiplied by essentially what I'm saying is that the area under this triangle is exactly the same as this, and so then again 1 multiplied by the disparity gives us the area, right? And this is very good because the area is just a summation, so it's differentiable, and we can use it as to then both estimate the disparity and train the network. You could argue that you could also use some zero crossing network that finds the point where this line crosses the 0.5, right? The 0.5 mark in terms of probability. And we did think about it, but sometimes you do get you know, not as ideal distributions like this one. And what would happen here if you use the zero crossing method is that the first time that the probability drops before 0.5, you would identify that as the actual disparity. And note that in this case, all that happened is that for two different disparity levels, we made a mistake, and what that does, it just moves the estimate of the correct disparity back by whatever area we're losing, right? So it introduces an error, but it's not a major discrete jump from the correct disparity all the way to a different disparity. It's rather like just a little bit of noise. And so from the method I was describing before, we just add this area under the curve, we have some refinement, and then we can just train with a loss between the ground truth depth map and the depth map that we estimate with this. And so what does this look like? Now, we say continuous, but of course we can only sample at discrete disparities. So we sample quite densely, and we get a nice continuous depth estimation, which is comparable with state-of-the-art methods in terms of quality and results from the benchmarks. But we can also, going back to what I was describing before, we can also sample with the same level of, you know, just as finely, we can sample just a range, right? This is the parking use case that I was showing before. Now, note that we could do this with a standard method too, but if the value of the pixel, if the depth of the pixel was not in this range, then it would still be mapped to this range. In other words, if you look at this result, which is the result of our method, we get depth for the pixels that are in this range. And then we get some information for the pixels that are outside. In other words, we know that these pixels are closer, they're white, and these pixels are farther, they're black. So we don't know where they are, but we know that they are not in this range, and we know on what side of the range they are. In comparison, a standard method would place pixels on the sky, for example, somewhere in this range. So you would see the colors wrapping around in these regions. Okay, so let's look at the video sequence because videos are more compelling. Here, I'm showing the 4 types of results that I described today, which are binary segmentation, where the plane is put somewhere in front of the car by, somewhere around here. And you can see, this is actually the confidence map. You can see that there's non-binary values. And you can see that you can detect when objects get closer to you than a certain distance, right? So this is very useful. You can think of this as a virtual geofence that you put some distance in front of your car, and it alerts you of when an object comes close enough that you need to take an action. Of course, you can see that we can estimate traditional depth maps that are continuous over the whole range. Here I'm showing a very coarse quantized depth, which again, it's much faster than real time and much faster than existing algorithm, and it still gives you some information about what's going on in the scene, right? And then this is selective range, where it's similar to the application that I just described. It just gives you high quality depth. It allocates all of your budget of computation to a specific range of interest, and it tells you at least a little bit of information outside of that range. And this is really the key, right? What this method allows is for you to go out in the field and say, hey, right now I need high quality everywhere, and I'm willing to pay the price for it. And now I'm driving a different scenario. I want much faster execution, much lower latency, and I'm willing to take a little lower quality. How much lower? Well, it could be quantized depth, like in this case, or just this binary geofence at some point in the camera, like in front of the camera, right? In fact, we can actually get creative and say, okay, let's take our car and let's say that we really care for a region right in front of the car, as shown by this green rectangle, and we want high quality depth there. And this is what we would be seeing right here. This is the continuous depth estimation from in front of the car to essentially in this green box. However, we don't want to be literally short-sighted, nearsighted. You want to know before something crosses this region as early as possible that there is something, that an event happened, something crossed some safety barrier, virtual barrier. And now because of that, you have to spend more computation and expand the area of high resolution for the depth all the way to that safety virtual wall. So let me show how this works. Like you can see that as soon as the pedestrian, we also have an ROI just to make sure that the objects that are detected are within the area where the car is going. But you can see that as soon as the pedestrian crosses this safety line, now all of a sudden the depth gets expanded all the way, so we have much higher quality information for a larger range, right? And again, this is done at inference time. You don't have to retrain anything. You don't have to use multiple different models. Everything is trained independently of any of these factors. Let me show you another example, I think. Yes. So here you can see that when the cars come close, or to come closer than comfort, too close for comfort, then the depth estimation gets expanded all the way to the safety distance. And so I hope I convinced you that depth estimation from, well, I didn't have to convince you that depth estimation from images is an important. It's very important to be able to estimate. I hope I convinced you that we can deal with very challenging situations, even when the scene is dynamic, or even when we have a tight time budget that may be time varying. So it may vary over time during the deployment of the same algorithm. We can deal with those situations and solve for depth from RGB images. And this is the end of my talk. So if you have questions, and these QR codes are links to the websites of the papers.
All right. Thank you so much. Thank you, Orazio, for the wonderful talk. I mean, you definitely convinced me. I think those are really powerful tools to estimate the depth and from all sorts of data like RGB and also maybe stereo images. I see some there are some questions coming from the audience. But maybe before going to the audience question, can I ask like two quick questions, maybe one for each of your very recent work on CVPR this year. Yeah, but maybe some of them are really details. Maybe I should read the paper, but since you are here, I just want to get some quick verification from you. I think for the first work, right? I think you're introducing like some really multi-channel neural networks where you're taking into account of using both the RGB images and also, I mean, a single image and also some rough estimation of the depth, maybe from other algorithms. But I'm just curious because for most of the multi-channel neural networks, you need some kind of a fusion module eventually, right? Because I saw in your plot you have some specially designed module to kind of fuse multiple features. Is there anything special, or what kind of fusion scheme you use in that? For that module?
Yeah. So you're talking about this, right?
Yes. Exactly.
So for the most part, the fusion is implicit. What we do is we concatenate the RGB image with the single image depth, and we concatenate the RGB image with the multi-view stereo depth. And then
I see.
We use the same. We use an encoder for both. And then what we do is in the bottleneck of this network, we just concatenate the features from the multi-view stereo depth and the features completely from the single image depth, and then we just feed them the concatenation of those two to the decoder. That's the way we do implicit fusion of the two. Yeah.
I see. Yeah, I mean the reason I ask is because I came across your other work on PSE-net, where you have a specially designed fusion module rather than feature concatenation. I was wondering whether those tricks will kind of help for this task specifically. Have you ever compared different way of fusing the features?
We didn't. That's a very good question. We didn't run the experiment, in part because we tried this and this worked, and so it seemed like it wasn't necessary to move to other strategies. But I think you're right. Maybe there's something to be gained there. Maybe that could also help with regularizing better between the multi-view stereo depth and the single image depth estimation.
Mm-hmm. Cool. Yeah. I mean, look forward to that. Okay, so another quick question is actually about your second work on the stereo image for the depth estimation, right? Because I think I may miss some of the details since you mentioned that you have this very specially designed loss function for the binary segmentation part. And you mentioned that part is actually specially trained. But I didn't get it. So you're saying this is not trained end to end?
No. Sorry, I can see how the way I described it may have caused confusion. It's actually a fairly standard way of doing it. Think about it this way: when you have a data set of stereo pairs with the corresponding depth map, you can threshold the depth map at any level, at any disparity level, and get essentially what we're trying to achieve, right? A binary map that says what's in front and what's behind, right? And all that we're doing is we're using a binary cross entropy loss, which is a standard loss used for the task of binary classification. And we compute the binary cross entropy between the ground truth binary map that we generate by thresholding the ground truth depths and the output of our network. So it's just as simple as that. Now, this is for the binary depth. Because for the binary depth, the goal is just this, binary classification for each pixel. Then what I think I said that confused you is that when we go to the full depth estimation here. Now, the output of the network would be here, right? Would be, this is effectively the network for multiple Ds. When you combine all of them, now what you have here is, so this volume, this regularized and upsampled volume, what it is a stack of all of those binary maps, right? And I guess you could treat each of them independently and do a cross-entropy loss, binary cross-entropy loss between each of those layers and the corresponding single binary map from the ground truth. But really what you want to regress here, you want to do regression on depth. And so what we're doing here is saying, okay, you have this type, if you go along 1 pixel along the volume, you have this type of function. How do you extract from this function, which is the output of the last layer, how do you extract depth in a differentiable way? And the area under the curve is a differentiable and we think sensible way of doing it. Does it make sense more sense now?
Yes. I mean, actually, one last concern I have is because eventually you're going to use this for your final goal. I mean, your final goal is to estimate the depth, right? And because since you have this differentiable loss for, I mean, particularly for the segmentation part, have you ever tried, like, say, you can actually introduce some kind of hybrid loss? I mean, maybe not only using this differentiable loss alone, but maybe somehow combine with the so-called true loss for your depth estimation. I'm just curious how these two are, or maybe is it possible to kind of apply both of them?
Well, so the output of I guess what I'm trying to say is that your ground truth is depth, right? And the output of your network is not depth. The output of your network is a function that looks like this.
I see.
How do you compare them? Well, the only way that I can come up with is if you take this and you extract depth from it. But you have to do it in a way that is differentiable, right? And so I cannot really think of other ways. So one thing that we did think about was to take this and treat the problem as a zero crossing problem, right? And say we can train a small multi-layer perceptron to find that crossing, and then the network, because it's a network, is differentiable, so you can use it as a differentiable operator. But there are issues. One is the one that I mentioned that is much more sensitive to errors, and second, the area under the one thing that I didn't mention is that the area under the curve is independent of the number of disparity levels. Whereas if you train something like a multi-layer perception, then you're stuck with a specific number of disparities that you're testing, and then you need to retrain for a different number of disparities.
I see. I think now I get it. So it's something like it's an indirect way of how to say measure the depth accuracy, but that may be the more reliable way, like we explained. I mean, this way you can get rid of some kind of possible troubles, like some example you show, right? But still, that's a way to reflect the actual depth. All right, thank you so much. I think I got the the really good clarification. Maybe now we should go through the question from audience. So I think the first question is coming from Shiraz. So Shiraz, are you still there? I mean, I try to enable you to chat. Okay, let me see.
So I'm reading the question while
oh, sure.
So it seems like Shiraz is asking about the first project, and he's saying that I think he's right. He's saying that if you only look at a single image, you're making strong assumptions about the priors on the image, right? He's making the example that if a tree and a person are the same height, you assume that the tree is behind, but you're going to make mistakes because maybe the tree is smaller than you imagine. And that's true. And that's precisely the limitation of single image depth estimation. In fact, sometimes some of these algorithms do overfit to a specific data set. And you can see that by like, applying small changes to the distribution of the data, and you see completely wrong results. So you're right. That's an issue. The question is, what is the problem that issue generates? For single image, in general, for the most part, those priors, so long as you use a very large data set to train, those priors are going to be fairly accurate more often than not. That's why the network learns it, because it's the most common scenario. And so it won't be a big deal, because it's just important that whatever, in the example of the tree and the person, that they are relative to each other, they are in the correct ordering, right? If you want to use that information for to combine multiple images, now they need to be consistent across the multiple images. And that becomes a harder task for single image estimation, which is why we combine the multi-view stereo information as well to address exactly that problem. I think that's answer to his question, I hope.
Yes. Yeah. I mean, somehow I cannot enable the audience to talk. But I guess we can actually read out the question, right? Then provide an answer perhaps. Okay. So yeah, I think that's the response to Shiraz, and perhaps we can go to the next one. Okay. Next one is from Varun Kalka, I think. Okay, so he's asking, like, in the first set of results, the proposed algorithm shows some, I don't know, blurred around the depth of the moving objects. So what is the reason for that? He assumed that the segmentation boundary are accurate enough.
Yeah, that's Kenai. Yes, there are some artifacts of the boundaries, and that is exactly due to the fact that we are blending these static and dynamic. So maybe I can answer this question by, I didn't want to dwell too much in the way we fuse the images, because I didn't think it was as insightful, but if I can bring it up, maybe I can explain that better. I don't know why my PowerPoint is not cooperating.
I can still see your sharing.
Yeah, I'm trying to go to a different slide and it's about to crash, I think.
Okay.
Yep,
do you want to like reshare it?
Maybe while it starts, because PowerPoint is crashing. So I'll stop sharing for a second. The answer is that we fuse this information, the dynamic background and the dynamic foreground and the static background with these masks, and in the process of fusion to avoid creating sharp artifacts between the boundaries, we introduce a little bit of blur. And so it's a mix of how we perform the blending and the accuracy of the segmentation masks. That's the answer to.
Oh, cool. Okay. Hope that address the concerns from Varun. And then let's move to the next question from Daniel. He's asking, like, okay, he's asking to go to the page of the columns of images labeled. Well, then unfortunately you cannot, get back.
What is the question? In the article on the top image, if you jump on the step, notice the windows showing greater depths. How is that so? Why? Okay. Let me see if I can pull it up quickly. My Outlook restarted. I think what it's looking at is this. And let me share my screen again. Screen one. Okay. Yeah. So I think that the question is about these regions being classified as a little farther. It's true. They are the result. So it's I guess it's well. Actually, if you look at the windows, they are a little retracted with respect to the wall. So it may actually be correct. Like if you look at this region, you see that there's a few inches between the wall and the actual windows. So it may be correct. It may be due to the inductive bias of the network. If it is wrong, it just so happens to be kind of like on the farthest plane. So a mistake will generate a small shift when we do the rendering and overview, but it will not be very apparent. So yeah, so the answer is, if it is a mistake, which I'm not positive, but if it is a mistake, it's due to, it's a failure case, I guess, and because it so happens to be on a far plane, it shouldn't have that much of an effect on the result.
All right, so okay, let's move to the next question. This one is from Shailesh, and the question is how the target velocity effect the depth estimation. Okay, he's asking how is the target velocity effect of the depth estimation, how we can evaluate that. Maybe he's asking more about like the video one, I guess.
How the target velocity effect of the depth estimation. I don't know if he's talking about the first or the second project.
Yeah, my guess is maybe he or he's talking about the kind of the blurry artifact caused by the video, or sorry, caused by the moving object.
Yeah, I don't know. So if I would assume that it's related to the first talk, and that one way to interpret this question is maybe that I showed results where there was a limit to the maximum velocity of each object in the scene. And if that's the case, then I don't know. So then I actually don't quite understand what the question would be. I'm sorry.
All right. So yeah, perhaps we can. I mean, Shailesh, if you want to give some clarification of your question, you can post another one, but maybe in the Q&A session. Unfortunately, I mean, somehow the system doesn't really allow me to unmute you and ask question live. So yeah, I mean, if you want to maybe give more details regarding your question, you can maybe leave another one in your Q&A session, and then we can get back to you after the next question, perhaps. All right. So then we move to the next question from Dan Weller, and he's asking. So thank you for the excellent talk. So how variables are how variable are the lighting conditions in your data set you use to evaluate your by 3D stereo depth estimation method? So could the quantized depth map also be an advantage under the adversarial lighting, such as in glare or low light condition?
That's a good question. So the answer to the first part of the question is they're not very variable. So we use the two data sets. One is flying things and flying chairs, the scene flow data set, and that is a rendered artificial synthetic data set, which has absolutely no lighting variations. And then we also tested and fine-tuned on the Kitty, on the Kitty data set, which is a bit more varied. I think that there is a point there. So I think that the question comes down to whether estimating the direction of the disparity as opposed to its magnitude is more robust, and we think it is. So as a person, as a human observer, when you look at these images, if you look at two disparity vectors, it's difficult to say how long they are exactly, right? Which is the magnitude, but it's very easy to see whether they are flipped with respect to each other, right? And that's what our algorithm is doing. So in that sense, a more challenging scenario could be dealt with better with quantized depth, because the feature that we look at is easier to classify. I don't know if glare and adversarial lighting is necessarily something that we could solve, though. I think that we still, the underlying principle that the network looks for is still some form of correspondences, some form of implicit correspondences. So the fact if the surfaces are not Lambertian, it may still be an issue. We have not tried. We would have to look into that. Maybe.
All right. I think there's another new question coming up from one of our audience, Debashish, if I pronounce correctly. But I didn't quite get the question. So he's asking, like, in general, is it Bayesian or classical estimation? My guess is that he may refer to the, I don't know, competing method or what, the baseline.
I don't know. It's not Bayesian. Neither of the methods that I described is Bayesian, although I'm sure we can find a formulation, a Bayesian formulation that could approximate them. So maybe I would say classical. It's a big general question. I don't.
Yeah, it's kind of like too general. Like we don't know which one you're referring to. But yeah, I think that's it for all the question we have tonight. But of course, oh sorry, there's another one. Wait, I think that's from Dewala. He's okay. He's not asking question. He's suggesting that it's a good idea. But
yeah.
Okay. Yeah.
Yeah. So he's just to read it out loud for the rest of the people.
Yes.
He's suggesting that this is an important thing to test because it would be a major limitation of existing in-car collision warning and active braking systems, and I agree. It's something that we need to test further.
Yes.
And we are actually, internally at Nvidia, we're actually looking at safety for stereo with this solution. So you may hear more about this later.
Yeah, I think that's a good point, and all right. So I think that's it for all the questions. And again, I mean, thank you, Orazio, for giving us the really wonderful talk, and thank you for the really good sharing for your recent works. And also thank other attendees and participants to join us for this wonderful talk. I think that's the end of today's webinar. And also, I think our webinar is actually regularly for every 2 weeks. So you're more than welcome to join us, the week after next week for the next speakers. And hopefully we can see you all next time again. All right. So that's it. Thank you for all you guys.
Thank you for inviting me. It was a lot of fun.
Thank you, Orazio. You have a nice day in the Bay Area.
Bye.
All right. Yeah. You should have a good night. Bye-bye.